The icy comets are the leftover bits and pieces from when the solar system formed so long ago. And these pieces are frozen in time, and they're important to us because we probably wouldn't be here without them. Well, going into the mission, we thought that perhaps this comet and other comets as well were sort of dirty ice balls, sort of like a snowball that you would make and pack it real tight and then jam in some stones and rocks and stuff. Nasty little snowball. Jet black.
The thing that's really cool about this mission is there's nothing subtle about deep impact. It's something that anyone can understand. We're trying to smack a comet as hard as we can with a hunk of copper. We'll be going about 23,000 miles per hour, and we're going to watch what happens. And we actually get a surprising amount of excellent science data from this impact. We don't know what the interior of a comet is composed of. We don't know whether it's densely packed or loose, and we're going to learn a lot about that from this impact.
This is a first of a kind, and it's really exciting because what we're trying to do is not only hit the comet with an impactor spacecraft, but to also have a second spacecraft watching and seeing the impact at the same time and taking the pictures of the crater formation and getting the science data that's really behind this mission. So we like to equate that to a bullet hitting a bullet and another bullet trying to look at the same spot at the same time. We expect that deep impact will create a crater that will throw this dust up into the sunlight so we can actually get the pictures and the spectra of what that dust and material, that debris coming out of the crater actually is.
We have a prediction that we will excavate a crater the size of a football stadium in about 200 seconds. However, the research community disagrees on the nature of comets. They disagree on how they're held together, and they therefore disagree on what the cratering process will do, and therefore on what kind of a crater we'll get at the end.
That was a night. July 4th, 2005, our nation's birthday. It was white-knuckle time because we were trying to hit this comet at a speed of 23,000 miles per hour at a distance of 83 million miles away, and so it wasn't easy.
Bring us up to speed on what's happened thus far.
Well, we've reached a very exciting point in the mission. Obviously, we're in the climax right now, and AutoNav, for the first time on the impactor, is computing a solution, trying to figure out exactly where to target to on the surface of the comet.
We just got through performing the first of the 3 impactor trajectory maneuvers. Right now, we're getting the data back on the performance, but it looks really good.
What you're looking at is the high-resolution imager has sent down those 8 different images in the 8 different filters.
All stations, approximately 10 minutes to the start of AutoNav image processing. ADCS, you're on your own.
Copy.
This is the control room. We had report back that our final impactor targeting maneuver was just basically right on, so everyone's pretty excited at this point.
Go ahead.
We are turning to the burn attitude, target ID 6.
Copy, thank you. About 20 seconds to impact.
Flight, this is Telecon. We have lost a block.
Team, we got a confirmation.
Oh my God, look at that! When it actually did hit precisely where we wanted it to, there was this enormous explosion, and the dust and the debris that came up said rather emphatically that this was a big success.
Right now we're -1 spacecraft, the impactor. It's been totally vaporized per plan. And you can see it all the way up to the end. We had a requirement to get a picture about 30 seconds out from impact, and what you saw here, we got the last picture was 3 seconds before impact.
Obviously, it was a very big impact. There is a lot of topographic relief. There are things on this nucleus that really do look like impact craters to many of us. Almost certainly there is layering.
For a small object like this one, at least on a celestial scale, you would have expected the object to be fairly uniform from end to end. That is, this side would look pretty much the same as this side. On the surface of this comet, Tempel 1, we had an area that had impact craters. There were round craters that were formed as a result of probably asteroids coming in to smack the comet from time to time, that are indicative of a very old surface, surfaces that are millions of years old. And just right next to it, we have a very smooth area that is indicative of a very young surface, because a smooth area doesn't stay smooth in space very long because of these impacts of asteroids. We've got some mechanism, perhaps outgassing, that drops material down onto the surface and makes that area smooth. We just don't know.
Few telescopes reported big increases in the emission lines in the spectrum. Both ground-based and Hubble observed that kind of brightening, so they're getting lots of results also.
So whereas the spacecraft was actually taking more or less a snapshot of the central portion of the comet, it was left to the ground-based astronomers to study the comet's development over a long period of time. That is, they studied the comet before the impact, during the impact, and after the impact. They had far more instrumentation available to them than the deep impact spacecraft could carry, because the spacecraft was carrying the impactor. We think the basic properties of a cometary nucleus, at least to the extent that Tempel 1 can be a proxy for all comets, is that comets are basically very fragile. They're very fragile in the sense that if you took a chunk of the comet's surface, you could break it up easily with your hands. They're very porous in the sense that 70% of the comet is void space. It's sort of like a sponge with a lot of pores in the sponge. The only problem is we don't know whether the pores are tiny, with many of them, or whether they're large with just a few. It's much less dense than water, so if you had a pan of water large enough, this object would actually float. A question that scientists often ask about this mission and Comet Tempel 1 is that was the cometary nucleus homogeneous? It's the same stuff throughout. And was it made of cometesimals? Is the main comet made of little bits and pieces, say 100-meter sized blocks of material? Well, no and no. The comet is not the same from end to end. It's not homogeneous. It's layered, at least on the upper surfaces anyway, and so that suggests that it's not made of these chunks or cometesimals, but it's actually made of thick layers or slabs of ice and dust piled one on top of another like an artichoke. One of the more important investigations involved with the Deep Impact mission was an attempt to understand the so-called primordial ices that make up a comet. What was the nature of the ices and the material from which comets formed in the outer solar system some 4.5 billion years ago? So when we got there, we found water ice in abundance. Carbon dioxide ice, dry ice, was there in much less proportion, and those were the two main ices. Now, in terms of the minerals involved, the embedded dust particles in the ices, some of them are silicate materials, sort of like beach sand, olivine and pyroxene we call them. They must have formed in the inner solar system where it was very hot. Some of the materials that were found as a result of the Spitzer Space Telescope observations are called carbonates and sulfides, and they must have formed in sort of the mid-range of the solar system. And some of the materials, the ices, formed in a region that was quite cold in the outer solar system. So Comet Tempel 1 is made up of materials from the entire solar system. And that was a surprise, because initially we thought that the comet would form from materials that had always been in the outer solar system. What's the bottom line on this mission? Well, Mother Nature's sort of pulled the rug out from under us in a number of different respects. So when you can go there with your preconceived ideas and theories and test them with ground truth, with the spacecraft being there and finding out what actually is the case, that's really the essence of a great mission.
I just look forward to a wealth of data that will take me to retirement.
I obviously hope that it's made America proud to see that we overcame a lot of challenges and the team stuck together through a lot of adversity and problems to work out and made it happen, and it happened like clockwork, and I think that's something to be proud of on America's birthday.